Welcome to this lecture series in linear algebra. In this lecture, we will discuss the notion of complexification of a real vector space, and we will deduce some interesting results about real vector spaces using that concept. In particular, we'll prove that every endomorphism on an odd-dimensional real vector space has an eigenvalue. So, of course, we will need to know what are the definitions of eigenvalues and eigenvectors. We will make use of the fact that every endomorphism on a complex vector space has an eigenvalue. And this fact, which we have seen many times, is that if we have an endomorphism on a vector space V, nothing to do with real or complex vector spaces, just an arbitrary field is required. So fix an endomorphism on a vector space V, and let this be a T-invariant subspace, which means this. Then we have this diagram which commutes. So this endomorphism T gives rise to this endomorphism on the quotient space. So what is this map pi? This map pi takes V to the corresponding coset, and T bar takes coset of V to coset of TV. So we have seen this many times, and let us proceed. Here are some problems for practice. And now let us get started. So fix a real vector space. We will define a complex vector space structure on this Cartesian product. There is already a real vector space structure here, namely that of the direct sum. So this as a set is same as that, and therefore there is a real vector space structure here. But we will endow this with a complex vector space structure. And for convenience, let me call this W. So to define a complex vector space structure on it, we need to define an addition map. And how do we define it? We just add component y's. A natural definition of addition. But the scaling part is interesting. So the scaling map is defined as follows. The complex number alpha plus I beta, where alpha and beta are real numbers, scales the element u comma v as so this seems quite mysterious, but let me explain. We are thinking of this ordered pair as this. Of course, this is not some formal object, but in our mind, we are thinking this guy as that guy. And therefore, if we were not told anything and were asked to scale u plus iv with alpha plus I beta, just by high school kind of bracket multiplication, we would have written this. If you open the brackets, you would have found that. Of course, this is not formally meaningful because this is not formally meaningful, but this is the idea. This part comes here and that part comes there. So that is what motivates this definition. Okay. One should now check as an exercise that with this definition of addition and scaling, this quadruple is a vector space. Okay. This is called the complexification of V. So we have obtained a complex vector space out of the real vector space V. And as an exercise, one should also show that the dimension of this space, of course, let me just put a subscript C to emphasize that it is a complex vector space, is same as that. This may seem trippy, but it is not. Because this is a complex vector space, its real dimension is twice of its complex dimension, if that makes sense. So this equation shouldn't confuse you. In fact, what you can show is that if V1 up to Vn is a basis of V, then this tuple is a basis for W. Okay, so make sure you understand these blue statements. And so far we have defined the notion of complexification of a real vector space. We can also complexify endomorphisms. So suppose we have an endomorphism on V. V is, of course, this real vector space over here. So define T tilde for a lack of better notation. T tilde from the complexification of V to the complexification of V. So it is an endomorphism. I mean, we are going to define something which will turn out to be an endomorphism. The definition is it takes a vector W to this thing. Just apply T coordinate wise and check that T tilde is complex linear. Complex linear, and hence, which in other words is just saying that T tilde is an endomorphism of W. Okay, and T tilde is called the complexification of T. So we can complexify vector spaces and complexify real vector spaces and complexify endomorphisms on them. Okay, so now let us proceed to exploit this in order to prove some non-trivial results about real vector spaces. So fix a real vector space and an endomorphism on it. Then we will show that there is a T-invariant subspace of V, call it U, such that the dimension of U is either 1 or 2. In case of complex vector spaces, we showed that every endomorphism on a complex vector space has an eigenvalue, which is same as saying that it has a one-dimensional invariant subspace. Here we have something weaker, but not very weak. We are able to show that there is a T-invariant subspace of dimension at most 2. Okay, at most 2, but at least 1. So let's prove this using complexification. So W be the complexification of V. And T tilde be the complexification of T. All right. And since every endomorphism on a complex vector space has an eigenvalue, we can pick an eigenvalue of T tilde. Okay. Since this is an eigenvalue, there exists some non-zero vector in W such that this is equal to the scale of the vector by our eigenvalue. Okay, and now we use the definitions of P tilde and of scaling in the complexified vector space to get this equation. All right, but this one equation is actually two equations, which is this is equal to that and this is equal to that. So this implies Tu is this guy and Tv is that guy, and this implies that span of uv is T invariant, right? Because the image of u is within this and the image of v is within this. So span of this is T invariant. But the dimension of this is at least 1 and at most 2. It is at most 2 simply because there are 2 vectors which are spanning it. And it is at least 1 because not both of u and v are 0. So we do obtain a vectors, we obtain a subspace of dimension at most 2 and at least 1, which is T invariant. So that proves this proposition. Okay. And as a consequence, we will now prove something very interesting, that if we have an odd dimensional real vector space, so fix an odd dimensional real vector space and fix an endomorphism on it, then this has an eigenvalue. So it is not necessary that an endomorphism on a real vector space has an eigenvalue. As we saw, rotation in 2 dimension is one such example. But on an odd dimensional vector space, that kind of pathology doesn't occur. And this is the linear algebraic analog of the fact that every odd degree real polynomial has a root. Just like the corresponding theorem in the complex world is the analog of the fact that every polynomial over the complex number field has a complex root. Anyway, so let's try to prove this. So assume on the contrary that this is false. Right, so if it is false for some odd dimensional real vector space, and we will pick one such vector space of smallest possible dimension. So let V be an odd dimensional vector space, real vector space of smallest possible dimension for which there is an endomorphism devoid of any eigenvalues. Right? So what are we saying? Since there is a counterexample to the proposition, there exist odd dimensional real vector spaces along with endomorphisms on them such that the endomorphisms do not have an eigenvalue. Amongst all such counterexamples, we pick one where the dimension of the vector space is smallest possible. Okay, now by the previous proposition, we can find a subspace of V which is T invariant such that dimension of U is either 1 or 2. But if dimension of U were equal to 1, then we would have a one-dimensional T invariant subspace and hence an eigenvalue. But since we have assumed that this is a counterexample to the theorem, we cannot have dimension of U equal to 1. So this we can just slash out. So dimension of U is necessarily 2. And now we will make our diagram, which we recalled in the beginning. All right. So what we have is, we have this vector space whose dimension is 2 less than the dimension of V, and hence this is also an odd dimensional vector space. So this is odd dimensional. All right, and we have an endomorphism. We have an endomorphism on that odd dimensional vector space. So it must have an eigenvalue by the minimality of the choice of the dimension of V. This, if T bar did not have an eigenvalue, this would be a vector space, a real vector space of odd dimension, but of smaller dimension than that of V, which furnishes a counterexample to the proposition. But this was already a minimal counterexample to the proposition in the sense of dimension, and hence T bar must have an eigenvalue. So let this be an eigenvector with eigenvalue lambda, corresponding to eigenvalue lambda. So this be non-zero. I write 0 bar to indicate that it is the coset of 0 in V mod U. So this is a non-zero vector in V mod U such that this thing is lambda times this for some lambda. So for some real lambda, this is true. But if we decode this equation, this says that tv plus u equals lambda v plus u. Okay. Which means that tv minus lambda v is in u. All right. But now we claim that this is not invertible. So why is it not invertible? So first, instead of writing this, I will write it in a different fashion. Okay. And now just think of this endomorphism. This is an endomorphism on V, but what is it doing? It first of all takes capital U inside capital U, because T takes capital U inside capital U. So maybe I should take a different page for it. Otherwise it will be all hodgepodge. So this is not invertible because T minus lambda I takes U to U, meaning the image of U is contained in U under it. And it also takes V to U. Why? Because of this. But also note that since V plus U is non-zero, V is outside U. So this thing is outside U. This implies V is not in U. So with that deduction and with these two things in hand, we see that T minus lambda I is a map from span V plus U to U. It takes span V plus U inside U. So it is taking a three-dimensional thing into a two-dimensional thing. Right? Because since V is not in U, this is a three-dimensional subspace of V, and this is a two-dimensional subspace of V. So this thing takes a three-dimensional thing inside a two-dimensional thing, and hence it must have a kernel. And that shows that this is not invertible, and hence T has an eigenvalue, namely lambda, which contradicts the choice of T. T was chosen so that T does not have an eigenvalue, and this contradiction establishes our theorem, and with that, we are done. So with that, I also want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.